We've been talking a lot about elementary matrices. A good question to ask is, are elementary matrices invertible? And the answer is yes. In fact, all elementary matrices are invertible. So what does the inverse of an elementary matrix look like? Well, let's say we have a type 1 elementary matrix. Remember that a type 1 elementary matrix, well, we take the identity matrix, which can be any size. Here I'm just going to use the 3 by 3 identity matrix. And we just switch any two rows. So here I'm going to switch row 2 with row 3. And this is an example of a type 1 elementary matrix. It turns out, let's call this matrix E sub 1. It turns out that the inverse of such a matrix is itself. Why is that? Well, if we multiply E sub 1 with itself, because this is an elementary matrix right here, what's going to happen to this matrix, E sub 1? Well, we're going to switch row 2 and row 3. So if we switch row 2 and row 3, we get the identity matrix again. And this is for any type 1 elementary matrix. So what if I switch row 1 with row 3? And I call that E sub 1, well, its inverse is the same matrix. So the matrix with row 1 and row 3 switched. Now what if I have a type 2 elementary matrix? What would the inverse of that look like? Well, let's see. So if we have a type 2 elementary matrix, let's give an example. Type 2 elementary matrix means I just take one of the rows and multiply it by a non-zero number. Here I multiplied row 2 by 2. What do you think let's call this E sub 2. What do you think the inverse is going to look like? Well, what's going to happen is you're going to write the same matrix, but where you the row you multiplied by that non-zero number, you're going to multiply by that non-zero number but 1 over it. Let's see. Let's check this. And remember, it doesn't matter the order. Of these two matrices if they're inverses of each other. Well, here I put E sub 2. This is the original matrix. And what does this, because now we're multiplying by this matrix. This is just a random matrix. Happens to be elementary matrix, but we can just think of it as a matrix. And now we're multiplying this matrix by an elementary matrix. And when we multiply it by a type 2 elementary matrix, we just take this second row and divide it by 2. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1. If you switch these, you would have 0, 1 half 0, and then you would multiply that second row by 2 because you would have the 2 here. So you get the same thing. So you can see that the inverse of an elementary matrix that's type 2, whatever you had, whatever row you multiplied by a non-zero number, you're going to take that same row and divide it by that non-zero number, and that will be your inverse. Okay, now what if we have a type 3 elementary matrix? Well, remember, a type 3 elementary matrix is where you add a multiple of one row to another. So let's say we add 2 times row 3 to row 2. That's a type 3 elementary matrix. Let's call this E sub 3. What do you think E sub 3 inverse is going to be? Well, it turns out that it's going to look like this one. So it's going to be a type 3 matrix. But wherever we put this added multiple of a row, we're going to put the negative of it. Let's check that this is indeed true. So E sub 3 inverse times E sub 3. Let's see what we get. So we're taking this matrix and multiplying it by an elementary matrix that says I take the second row, so I take this row, and I add -2 times the third row. So -2 times the third row would indeed give me the identity matrix. Okay, so it turns out that all elementary matrices are invertible, and if it's a type 1 elementary matrix, the inverse is a type 1. If it's a type 2 elementary matrix, the inverse is type 2, and if it's a type 3, the inverse is a type 3. And you can see that for any type 3 elementary matrix, now here I just gave you an example, but we could instead multiply this row by like -5 and add it to the first row. That's an elementary matrix, a type 3 one. And so you would just, for the inverse, you would put a 5 times that bottom row to the top row. So it's just like doing the opposite of what you did. So here we had a +2. For the inverse, we put a -2. So just to be 100% clear, let me give you another example, the type 3. So let's say we have this matrix T. Let's say it's a 4x4 matrix. In fact, let me put so this is a type 3 elementary matrix because I took this last row and I multiplied it by 5/3 and added it to the top row. Well, then T inverse is going to be the same thing but with a negative here. It undoes what we did previously. All right, let's move on. Here's an important theorem. If A is an n by n matrix, then the following are equivalent. And what that means by the following are equivalent, it means if you have one of these, then all of them are true. So if A is non-singular, in other words, if A is an invertible matrix, then this is also true, part 2, which is if we have A times a n by 1 column matrix and we get the 0 n by 1 column matrix, then X has to be the n by 1 0 column matrix. So A times X is equal to 0 has only the trivial solution, X is equal to 0. And A is row equivalent to the identity matrix. So if you pick any one of these, let's say you had number 2, if you had a matrix that was n by n, where you had A times X is equal to 0, and it only had this trivial solution, then that would imply A is row equivalent to the identity matrix, and also A is non-singular. And if you had A is just this part, A is row equivalent to the identity matrix, you could show number 2 and you could show number 1. So having any one of these implies that you get all the other ones for free. Let's prove this. Now we need to prove that for any one, you get all the other ones. So these are actually if and only if statements. How we're going to prove it is we're going to show that 1 implies 2. And then we're going to show that 2 implies 3. And the last step is to show that 3 implies 1. That way, if you get any one of these, so let's say I tell you that number 2 is true, you could show me that number 1 is true by going through 3 and then back to 1. Okay, so let's do this. Let's say that A is an n by n matrix and A is non-singular. Let's show that if A times x is 0, then it only has this trivial solution, x is equal to 0. So this is what we're showing. 1 implies 2. So we're going to say A is n by n and invertible. So what does that mean? There's an A inverse such that A times A inverse is the identity matrix. Now we're going to say there exists an x that's n by 1 such that A times x is the 0 n by 1 matrix, right? If we have A times x is equal to 0, what I want to show is that the only x that works for this is x is equal to 0. So we can't have any other column matrix that when we multiply it by the matrix A, we get the 0 matrix. So how am I going to do that? Well, if A times x is equal to 0, this is an n by n, this is an n by 1, this is an n by 1. I can multiply both sides by A inverse. And then these matrices are associative. This gives me the identity matrix. And any matrix times the 0 column matrix, as long as it's n by n, is going to be the 0 column matrix. So I get that x has to be 0. So we've shown that 1 implies 2. So this piece is done. Let's show that 2 implies 3. So what that means is we want to show that if A times x is 0 and it only has this trivial solution x is equal to 0, then this matrix A is row equivalent to the identity matrix. So let's let A be an n by n matrix, and suppose A times x is equal to the 0 matrix. How did I phrase it before? Has only the trivial solution. X is equal to 0. Now I want to show that A is row equivalent to the identity matrix. You might want to write to the side just to remind yourself what it means for something to be row equivalent. So maybe we can do that. This will help us figure out the rest of this proof. So A is row equivalent to the identity matrix. That means A is equal to some elementary matrices times the identity matrix. So since we have that A times x is equal to 0, well, this matrix A, I can make it an upper triangular matrix using elementary row operations, right? So if you have some matrix A, multiplying it by some elementary row operations, we can get it into reduced echelon form. Every matrix has a reduced row echelon form and a reduced echelon form. So let's just say that we're going to put this, we're going to multiply by some matrices, elementary matrices. Let's say there's L of them on both sides. This will put us in an upper triangular form. So we're going to have a matrix I'll write in just a second what this looks like. This is going to be 0. So what I'm saying here is we're going to have some matrix. We can put it in this form. Here I'm assuming that this is a 4x4 matrix. I didn't specify what size, but that's the idea. This could be an n by n matrix, but we can put it in upper triangular form. And the thing is, we're going to have n pivots. The reason for that is this matrix A has to have n pivots in order for you to have one solution. If it didn't have n pivots, let's say this was a 0 here, then we would have infinitely many solutions, right? And it doesn't say that there's no solution at all. So we have to have exactly n pivots. So this has n pivots in order for X to have one solution. Well, if it has n pivots, that means you can get it into reduced row echelon form, and the reduced row echelon form, because if it has n pivots, you can get rid of everything above, is going to be the identity matrix. So what we can say here, maybe I can make this a little bit smaller. We can continue to put U. So we took A and we multiplied A on the left by these elementary matrices to get U, but we can continue to multiply by elementary matrices to get the identity matrix. So then the identity matrix is a bunch of matrices like this, because I used L here, because this was the matrix U. And then I have some more, I think I should probably have used like J or something, because this letter actually comes after K. But the idea is I'm going to multiply all of these matrices together and I can get the identity matrix. So I can add some extra, let's just call this L plus 1. Maybe we should use the letter M instead. So there's a bunch of other matrices that I can get it to the identity matrix. So these matrices here correspond to the matrices here. So in other words, I is equal to some product of elementary matrices times A. So you can see that the identity matrix is row equivalent to A. And if you want to show that A is row equivalent to the identity matrix, well, each one of these matrices, these elementary matrices, because they're elementary matrices, they're invertible, which is what we talked about a minute ago. So we can say that we can get rid of each one of these by doing this. Let me show you. You could say EM inverse times I is equal to EM inverse EM E2 E1 times A. So that goes away, and then you're left with all the other elementary matrices, and then this part is just EM inverse. So you keep taking off the elementary matrices by multiplying by the inverse. So what you're going to end up with is that A is EM inverse times EM minus 1 inverse, E2 inverse, E1 inverse. Because I'm going to knock each one off, and the first one I'm going to knock off is EM inverse, then en minus 1 inverse, and so on until you get this last one and you're just left with A. And all of these are being multiplied by the identity, so the identity times any matrix is the matrix itself. So what have we shown? Remember we said before that if A is invertible, it's the product, the inverse is the product of elementary matrices. And it turns out that the matrix itself, the matrix A, is also a product of elementary matrices because all of these inverses are elementary matrices. Okay, so we've shown that 2 implies 3. Let's show the last one, that 3 implies 1. I'm going to need to make some space, so I'm going to do this here. Just make sure I have some space. Okay, let's show that 3 implies 1 and we'll be done. So 3 is A is row equivalent to the identity matrix. Let's show that A is non-singular or A is invertible. So we're going to assume A is row equivalent to the identity matrix. That implies that A is equal to some elementary matrices times the identity. Again, we can get rid of these elementary matrices by just knocking each one off. Let me show you. So we can multiply this by EK and we'll get EK inverse times EK and this will go away and we'll get the identity, and we're left with EK inverse times A is equal to EK minus 1, so on. And then you do it again. You get rid of this one and by multiplying by the inverse. So we get that A, if we multiply by EK inverse times EK minus 1 inverse all the way to E2 inverse times E1 inverse, this is equal to the identity matrix. So I'm just getting the identity matrix by itself. If we multiply all of these together, we get a matrix B. And we get that B times the matrix A is equal to the identity. And remember that the inverse of a matrix is unique. So this matrix acts as the inverse of A, so A is invertible. So we showed that because A is row equivalent to the identity matrix, that means A is invertible. And we're done with the proof of this theorem. Okay, great. Let's move on down here. So here is a corollary I just want to tell you, and we've already discussed this. If A is n by n and invertible, then A is the product of elementary matrices. We've already shown this. If A is invertible, then it's row equivalent to the identity. So A invertible implies A is row equivalent to the identity. That's from the theorem we just saw. So that means A is equal to EK times EK minus 1, E1 times the identity. But then anything times the identity is just itself. So we get that A is equal to this EK minus 1 all the way to E1. And you can see this is a product of elementary matrices. So A is invertible, it's a product of elementary matrices, and so is its inverse. Here's another corollary from the theorem. If we have a system that is A times X is equal to B, and the system has n equations and n unknowns, and the system has one solution, this is true if and only if this matrix A is invertible. So you have this matrix A that's n by n. Well, if it's invertible, then its reduced row echelon form is the identity matrix, and you can solve for X by multiplying both sides of this equation by A inverse. So if I give you a system, I tell you what A is, I tell you what the inverse of A is, you don't actually have to do all that work getting it to reduced row echelon form. All you have to do is take the inverse and multiply it with B, and then you will get the solution X. Alright, I think we are at a position now where we can figure out the inverse of a matrix in a hard way, which is using elementary matrices, and also in an easy way. Okay, so this is a matrix. We've seen this matrix before. We saw, I think, in the last video. I want to compute the inverse of this matrix. And this matrix is 3 by 3, 1, 0, 2, 0, 2, 4, 0, 1, 1. What is its inverse? In fact, we've already done this. We didn't actually write what the inverse was, but we wrote it as a product of elementary matrices. So I'm going to review what we did before. I'm going to show you basically the difficult route to getting there. And then we're going to find a quicker route, and they explain this route in the book. So here's the matrix A. How can we compute the inverse? Well, since A is invertible, I'm telling you it's invertible, it's row equivalent to the identity. And remember that if it's row equivalent to the identity, that means there's a bunch of matrices elementary matrices times the identity gives us A. So this is just A right here. So if we could figure out what these elementary matrices are and multiply them together, we'll get A. We've done this. You can look back in your notes. We said that this matrix A, if we multiply by 5 elementary matrices, we get the identity. And here was all the work. I tried to make it small, but we took this matrix. I'm not going to go through all of this again, but look, we took -2 times row 1 and added it to row 3, and then we wrote the elementary matrix. Here was the whole process. You can pause the video if you want and review it. So there were 5 elementary matrices, and then we found that the identity matrix is E5 times E4 all the way to E1 times A. And this product is A inverse. So if I ask you what's the inverse of this matrix, all you have to do is multiply these 5 elementary matrices together. And so that's what we're going to do. I'm going to multiply these matrices, all of them together. And so what would we do first to multiply them? Well, you can start however you want. Remember, matrices are associative, but I'm actually going to multiply these two first. And then we'll just continue down this line. Once we multiply these two, then I'm going to multiply these two. Once I find the answer to that, I'm going to multiply it with this one. And then once I figure out what that matrix is, multiply it with this one. Okay, so let's multiply these two matrices together. We get 1, 0, 0. Now this is elementary matrix. It says take 2 times the third row and add it to the second row. So let's do that. So we get -4, 1, and then 2. Yep, and then we leave the last row alone. Great. Now I'm going to multiply these two matrices together. And this says I'm going to take row 1 and add row 3. So I'll get negative 1, 0, 1, negative 4, 1, 2, negative 2, 0, 1. And then I'm going to take row 2 and add it to row 3. So let's see, negative 1, 0, 1, negative 4, 1, 2, negative 6, 1, 3. And then this says just take the last row and multiply it by negative 1/2. Oops. So this is negative 1, 0, 1, negative 4, 1, 2, and then positive 3, negative 1/2, and then, so let me try to make this look better. So we said this was 3, negative 1/2, and negative 3/2. So I claim that this is the inverse.